Okay. So a register may be assigned value only within a procedural statement, a task, or a function. Procedural blocks, a procedural statement can be inside a procedural block. In a procedural block, there are two kinds of them. Very long. Always block and initial block. So if you're going to declare a signal as a register, it can be assigned a value only inside the always block or inside the initial block, not outside it. Or it can be assigned within a task or a function. Tasks and functions are called subroutines in Verilog that we'll see later on. It's like a subroutine in any language that you might use. Function is just like a regular function, C language function. You can declare it once and you can use it multiple times, or you can call it multiple times. The same goes with task. Task can be declared once and it can be called for execution multiple times. We will see the differences and the details later on. But the register can be assigned only within this blocks. A register object may never be assigned by a primitive gate output or a continuous assignment. Primitive gate output or a continuous assignment is done outside the always block, outside the initial block. So a register assignment can be inside the always block or inside the initial block. It cannot be outside. That's why it cannot be done using a continuous assignment, or it cannot be mapped to a gate, primitive gate output. Primitive gate means basic gate, like an AND gate or OR gate, NAND, NOR gate, etc. Those are the rules for assigning values to registers. These are simple examples of registers A, B, and C. Now each of this is a single bit register. Here we can declare reg 15 down to 0, counter, comma, shift reg. So counter and shift reg, each of them is 16-bit register. We can also declare something like reg flops 8 down to 4. So this is actually a 5-bit register. Verilog supports this. So ideally speaking, it should have been 4 down to 0 for a 5-bit register. But Verilog supports this kind of indexing also, 8 down to 4. It's not a good design practice, but it is allowed by the language to do that. Then you can have an integer. Integer, as we have seen, it is internally a register of 32 bits. So we can say integer sum comma difference. So sum and difference, each of them is a signal of type data type integer. You can hold integer values. We can typically in a programming language, you might have seen that there are various functions and various ways to deal with strings or characters. Verilog is a hardware description language. So technically speaking, there is nothing called string or nothing called character. Everything is ultimately in binary data format, 0 or 1. And there is a way you can store a string in Verilog if you really wish to do that. There is no special data type for that. What we do is we declare a register. Each character that you have to store will need 8 bits. So if it is a 256-bit, reg 255 down to 0 buffer. So buffer is a register. The width of that register is 255 down to 0 means 256 bits. Divided by 8, it can store up to 32 characters. Characters means A, B, C, D, etc. String is made of characters, right? But this string called strings itself is made up of this character strings. So we can store such 32 characters in a 256-bit register. Why? Because for storing one character, I need 8 bits. Depending on how many bits are available, by divided by 8, I can store those many characters in the register that is declared here. Any questions here? Have you understood how string can be stored technically?
Yes.
So ideally speaking, in Verilog is not a programming language, as we have seen. So ideally speaking, we should not be having a requirement for characters. What you might end up doing is there might be a requirement when maybe you might be doing a UART design, the universal asynchronous receiver transmitter, to communicate with the PC or some other FPGA board or something. When you communicate with through a UART to the other side, there are certain characters that may be needed to be transmitted. So those characters are actually implemented in hex format, and you have to send the hex code for that. But in case you want to send actual characters A, B, C, D, E, F, G, H, whatever they are, they can be stored in a buffer and they can be sent. Do you, any of you remember ASCII table? Have you used a ASCII table for your programming anytime?
No.
Have you dealt with the ASCII table before? No?
Mm, no.
Okay, let me show you what that looks like. Okay, so if you can see this table here, is it visible?
Yeah.
Yes.
Yeah. So this is called a ASCII table, which you might use at some point of time. So for example, capital A to capital Z. If I want to send capital A for for example, if I want to display capital A on a LCD screen or a UART serial terminal, I have to send the hex code, equivalent hex code, which is 41. I cannot send A. I have to send the decimal code or the hex code. Normally the hex code is sent 41. If I want to send a small a, I should send the equivalent hex code, which is 61. If I want to send numbers 0 to 9, 0 equivalent hex code is 30, 31 for 1, 32 for 2, 39 for 9. And these are some of the other characters that which where the hex code is represented. Colon, semicolon, less than, equal to, greater than, question mark, etc. This is called a ASCII table. ASC double R, ASCII table, which you can Google it and download from anywhere. It's a standard table that people use, and specifically when you are interfacing with the LCD screen or when you are interfacing with the UART serial terminal, this is the thing that you have to refer to. To have A displayed in capital, you have to send 41 hex, then A will be displayed. Okay.
Okay.
So why am I showing you this? If I want to save A as a character in my buffer, it is better I save 41, because once the hex equivalent of A is 41, so I can directly save 41 in my register buffer and just send that. Because ultimately, even if I save A here, saving A also I have to send the save a equivalent hex number, which is 41. To remember, I can refer to this table. So A, capital A equivalent hex code is 41, small a equivalent hex code is 61, and so on and so forth, based on this table. Okay. So you can note down these points. Look at the ASCII table. You can Google it and download it. It will be found. You can look it up on this site or any other site. Just look for ASCII table. You will find it. And just mention this couple of points in your notes. Okay.
Yes.
Okay.
Okay. Moving forward. Now, as we have discussed, there are parameters in Verilog code which are basically constants. Why? Because I declare them once, it never changes. I just use it multiple times in my design. How do I do that? Parameter A is equal to 2 tick. The way this is pronounced is, or it is quite called out is A is equal to 2 tick B00. So 2-bit binary value 00. B is equal to 3 tick B010. So this is a 3-bit binary number 010. C is equal to 4 tick B100. So this is a 4-bit binary number. So parameter A is 00, 2-bit. B is 010, 3-bit binary, and C is 4-bit 1000. I can declare these parameters and similarly other parameters. For example, red size. Parameter red size is equal to 8, and I've declared it once, and then I use this label. This parameter becomes a label, so I can use this label anywhere or any number of times in my design. Red size -1 down to 0 temp. So temp is a register. And what is the size of temp? Red size -1. So 8 minus 1 is 7. 7 down to 0 means it's an 8-bit register. So temp becomes an 8-bit register. So imagine I'm using this red size, let's say 100 different places in my design. I declare it once and I use it 100 different places. If I want to change the red size from 8 to 16, all I have to do is go this one place where I have declared it and change it to 16. Rest of the places I don't have to change it because it's just a label that I'm using. So it will automatically detect my updated red size value, parameter value. So when you use parameter in the design, it's called parameterized design methodology. It is very handy in Verilog when you have to do wholesale changes or very higher number of changes in the design. And if you remember the AND gate example that we saw, we used a 2-input AND gate. We instantiated that 2-input AND gate 2 times and then created a 3-input AND gate. Do you remember that example? I think last lecture. Last lecture.
Yes.
So when you instantiate the design, the advantage with parameters is I can override the parameters of the lower level module. So let's say I've declared a parameter A in AND2 design. And then I instantiate that AND2 design in my AND3 gate design. So A initially was 00, but I can pass parameter A is equal to 01. So I can override the parameter in the lower level, which is getting instantiated. That's the advantage with parameters. You can override. Okay.
Okay.
So simple question. What's 00 is 00? So what is 010 equivalent decimal? What is 1000 equivalent decimal? 111 equivalent decimal.
2, 8, and 15.
So I want you to basically convert this binary number to decimal numbers. B, C, and D.
2, 8, and 15.
2, 8, and 15.
15. Yes.
Okay, any other answer?
It's D7.
D7. 2, 8, and 7. Is that it?
Yes.
Yes. Are you sure? 2, 8, and 7. That's the answer, right? Okay, so you're sure about it? Or any other answer?
Yeah,
Yes? No? So that's correct answer, right? You have to be sure about your answer. That's the reason I was asking you. 2, 8, and 7.
Yeah, it's 7.
Right. 8421 system, right? 2 raised to 0, 2 raised to 1, 2 raised to 2. 1 into 2 raised to 0, anything raised to 0 is 1. 1 into 1 is 1. 2 raised to 1, which is 2. 1 into 2 is 2. 2 raised to 2, which is 4. 1 into 4 is 4. 4 plus 2 plus 1 will give you 7. Again, 8421 system. 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. 1 into 2 raised to 2 cube is 8. 8 plus anything 0 is 8. 2 raised to 0, 2 raised to 1. 2 into 1 is 2. Rest is 0. 2, 8, and 7. That's a decimal equivalent for this binary numbers. Okay, so just keep practicing some of this stuff because you'll be needing it when you do design later on. Convert one format to other format, number format. So this is another example of parameterized design. We declare a parameter. Parameter is declared inside the module. So we declare a parameter inside the module and we can use it multiple places within the module. For Verilog, everything is inside the module. So the Verilog design starts with a module keyword, the name of the module, the input output port list, then signal declarations, always blocks, and finally at the end you'll see end module. You will see that? No, okay. Anyway, so this is the end module at the end of this. It ends with the end module keyword. So as I was just saying, everything is in a module. Everything is part of the module. So module can have module is connected to other modules using the ports on the periphery of the module. So what are the different kinds of ports that are allowed in Verilog? Input, output, and in-out, which is bidirectional. Inside, when you declare a port as input port, a net or a wire by that name is automatically created inside the module. You don't have to create a separate wire for that. When you declare an output, when you want to pass or send some value as an output to some other module or as a top level, you have to register it. Means you have to declare a separate register with the same name as the output port. And that register, if you're going to assign it within the always block, I mean. So if you're going to assign it within the always block, that output value there has to be an additional register with the same name, because without that the register assignment won't work. When it's an in-out type of port, bidirectional port, going by the input port rule, there is a net or a wire declared with the same name as this in-out port internally to the module. But you're going to send if you're going to send some data out, then you have to register it. Whenever you send some data outside the module, you have to register that port or declare a reg with the same name. When the data is coming inside the module, there is an implicit net or an implicit wire declared with the same name as the input port. You don't have to declare it separately. For example, the input port is called temp, for example. There will be a wire called temp declared internally inside the Verilog module automatically. Same with the in-out port. If there is a there is a port called temp, which is a bidirectional port in-out. The input part of the port there is a wire declared called temp implicitly within the module. Again, if I take the example, output port is temp. Now this is the output port, so the data is going outside the module. In that case, there will be an output called temp and there will be a reg called temp separately. And that reg temp can get assigned a value inside the always block. Only then that output declaration to the reg will work. If you don't do that, it will give you error. If you don't declare a reg with that name. Okay. So everything is part of the module in Verilog. This is what this slide shows. Inputs, because this is communicating with the external world. The external world could be some other module, some other top level design, or this itself could be top level design communicating with the outside world, some other board, for example. That's how data types or ports will work. Yeah, any questions here on the ports, how the ports are connected? Maybe you can draw this small diagram in your note.
No questions.
Questions? Okay.
Yeah.
Okay, so we go forward. Structural Verilog or structural modeling. Verilog modeling, modeling in Verilog is a very common word that you'll see because Verilog originated as a software simulation language, which was meant only for model creation or modeling. So everywhere you'll see modeling as a word being used. So modeling, there are two methods or two types of modeling in Verilog: structural modeling and behavioral modeling. Behavioral modeling is sometimes also called RTL modeling. Structural modeling is also sometimes called gate level modeling. But the main keyword is structural modeling and behavioral modeling. In structural modeling, if you look at a structural modeling method, we create a structure in Verilog based on certain other modules. So this, in this case, we are instantiating this and2 design two times. One, once the label is given A0, instance label is given 10, the label of the second instance is called A1. So this is a structural modeling method. And the behavioral modeling method is basically where we declare the behavior of the design. So in case of an AND2 design, we'll declare a behavior call of the AND gate basically. So rather than using a structural method where we instantiate gates or instantiate modules and connect them internally with the inputs going to some output, output going to some input, we'll describe the behavior of the design. That's a behavioral description or behavioral modeling. Modules inside the module is the main principal design entity in Verilog. Inside the module, you can have various other things. First, the module name, module followed by the module keyword, followed by the module name and the port list. The number of input ports, output ports, their names, whether it's input or output or bidirectional. So we have all that. Then there could be local wires, which are local nets, local registers, which will be used internally or used for output assignments. Any parameters for that module can be defined. One module can have basically instantiate other modules. So the module that you instantiate in your design will be a separate Verilog file. If you again go back to the AND3 and AND2 example, and 2 will be a separate Verilog file and 3 will be a separate Verilog file. In the and3 Verilog file, I'm going to instantiate my and2 design twice. But the behavior or the functionality of that and2 is declared in some other Verilog file, which becomes and2.v, for example. So, but one module can have other module instantiations. Typically speaking, you should not have one Verilog file having multiple modules. It is technically allowed, but you should not do that because that's not a good design guideline. If you're going to do design, it's always good to create separate Verilog file, each separate Verilog file for each module. It doesn't cost you anything. All it does is you have to create a separate file. It is much more structured for project management rather than having one file, one Verilog file having all the modules. Sometimes people do that, but that's not advisable. So that's what module does. Everything is contained in a module. Module name, port list, then wire definition, reg definitions, parameter definitions, any other module instantiations, etc. Okay.
Okay.
Yes.
This is an example. Let me shift this a bit somewhere. Yeah, okay. So this is an example of a 4-bit adder. Now this 4-bit adder actually is created using a single bit adder. If you look at it, this is a ripple carry adder. Means carry from one stage goes on to the next stage. Carry out of one stage goes to carry in of the next stage. Carry out of the next stage goes to carry in of the next consecutive, next successive stage. So this is a ripple carry adder. Each adder is single bit, but we cascade them to create a 4-bit adder, such a way that 4 input A, which is an input 4-bit input, and B, which is again a 4-bit input, can be added using these 4 individual adders cascaded in this fashion. Finally, I will get 4 sum outputs and 1 carry out. So there are 3 inputs A, B, and Ci carry in. A is 4 bits, B is 4 bits, Ci carry in is single bit. There are 3 inputs. There are 2 outputs, carry out, which is C3 in this case. C3 means carry out of stage 3. And there is some output, which is 4 bits. So now this is a digital circuit that I am going to build using Verilog using structural modeling method. Structural modeling method. So how do I do that? Let's look at it. Module, add 4. So you have to always give some synonymous name, or a name which is synonymous with this design. So this is a 4-bit adder, so I call it module add 4. A, B, C, I, S, C3, CO. This is my port list, out of which A and B are input ports, each of them 4 bits. Ci is an input port, single bit. S is the output port, 4 bits. 3 down to 0 means 4 bits. C3 is the output port, single bit. Then I have a wire called CO, which is 3 bits, which I need to connect this intermediate connections. 1, 2, and 3. So I need 3 wires. 3-bit wire called CO. Add. Now this single bit adder, I'm going to instantiate it 4 times. A0, where I'm going to call it first adder as label A0. The second instance of the adder is called A1. Third instance is called A2. The last instance, fourth one is called A3. C0 of A0, which is carry out, goes to carry out CO0. S of S0 goes to 0th bit of S. A is mapped to 0th bit of A. A is the input for the adder. B input is mapped to 0th bit of B. Ci is mapped to Ci, the incoming carry input. So this is the adder, first stage. Ci goes to Ci of the adder. A goes to A0 bit. B goes to B0 bit. S goes to S0 bit. C carry out goes to C0 bit. Second adder, A1. What is the input for the carry first stage? The output carry of the first stage becomes input carry of the next stage, which is here. The last associated value is the input carry. This is the first associated value is the output carry, which is first CO1, first bit of this wire. Then S of 1, first bit. Then A of 1, B of 1. So first bit of A goes to A, first bit of B goes to B, first bit of sum out goes to S1. CO of this goes to C input. CO, which is connected to 0th bit of C0, comes here as carry input. And C01, which is the carry out of this stage, goes out. Will become the carry input of the second stage. So CO1 is, for the first bit of CO, is the output carry here, which becomes the input carry to the next stage. The module can be instantiated. This is called a port mapping. Basically, we are mapping ports. The dot CO is the dot part, CO dot S dot A dot B dot CI, is the internal port names of this adder. So this A0 adder will have a separate module called add. Inside that add module, we'll have this port CO, S, A, B, and CI. So this is getting instantiated at one level above in the add 4 module, and we are creating this 4-bit adder. I can do this port mapping in this format or this format. This format of port mapping is preferred. This .co is the internal port name of that single bit adder, which is called a formal, and this is the actual, because this signal is the local signal at add 4 level. C0, for the 0th bit value. These are all the local signal at the add port level inside the bracket. Dot part, dot co, dot s, dot a, dot b, and dot ci are the port names inside each single bit adder module. If I do it this way, I can change the what do you call the sequence. I can also put C actually inside the module of add module. They are declared in this fashion. This sequence: carry out is first, then sum out, then A input, then B input, and carry in. This is how they are declared. But if I use this method, formal and actual method, I can change the sequence. I can put CI first, CO last, etc. The second, third, and fourth instantiations of the adder, I'm using a shortcut method where I don't have a formal, I only have an actual. Because I'm assuming I know what the formal sequence is inside the add mode. First is the carry out, then the sum out, then A input, then B input, and carry in that adder instance. So instead of using the formal, I'm only using the actual signals, which is at a local level. The same shortcut method is used for second, third, and fourth instantiation. This is allowed, but this is not preferable. This is more preferable. Sometimes you will forget the sequence in which, or many times you will forget the sequence in which this adder module internally has this ports declared. You won't remember, or somebody else has given you that design. You don't remember that. This is the right way to do it. So even if the sequence get changed for some reason, CI comes first, CO comes last, still your signal mapping or your signal connections won't be wrong. It will be done in the correct way. So I instantiate this module, adder module, single bit adder module 4 times. I create this design, then end module. So 4-bit adder is created using single bit adders which are instantiated 4 times in the design using structural modeling method. Do you understand this? Any questions?
Uh, yes. The only question is for the add zero, you mentioned dot .co and CO of O, and for add one, you directly mentioned CO of one.
Yes.
Can we also mention add zero similar to the way as add one?
You can do
Is it
that. I've
mandatory
just
to do?
deliberately done it to show you 2 different methods of doing port mappings.
Okay.
But this is a more preferable method. This is not preferable. This shortcut method.
Okay.
Why? Because in this case, even if my sequence of ports gets changed, still my signal connections will be correct. Because I will always use .ci goes to ci, even if I include it first in the port map.
Yeah.
So this is always a better method. Since you're going to start Verilog design, always start with good, habits. So it's always good to form the right habit rather than using shortcut methods. But this is allowed in Verilog. If you want to do it, it is allowed. Okay, so you can note down this design. I wanted to write it down. So whatever designs we will see now and going forward, slowly start creating a Verilog file. I wanted to write it down so you will practice writing now and then later on typing it and create a Verilog module out of it. So later on, once we see the test benches, by the time we reach the test bench stage, you will have a few modules ready in Verilog. So what you do at that stage is create test benches for the existing modules that you have already have ready. Once the module and the test bench is ready, then it is easy for you to do a simulation because the design and the test bench will be ready for simulation testing at that point of time. Okay. Let me know when you're done so we can proceed.
I'm done.
Uh, 1 second.
Yeah.
Yes, I'm done.
Done. Okay. Now this example of adder we have seen using structural modeling method. So can we do it using behavioral model? So let's look at an example for that. This is a behavioral. This is a full adder circuit. There are three inputs A, B, C, I, and there are two outputs, sum and C out. And this is a circuit for that. So I want to develop this full adder circuit using behavioral modeling method. So let's look at this example. Module F adder, full adder 4 is the name of the module. Sum, C out, A, B, and Ci. This is my port list, out of which sum is output port 4 bits. C out is output port single bit. A and B, each of them is the input port 4 bits. Ci is the input port single bit. There is a reg called sum, which is the same name as the output, 4 bits. There is a reg called cout, which is the same name as output port cout. Why? Because this sum and cout outputs will be assigned inside the always block. And as the rules go, we have to declare a reg for that with the same name as the output port and the same width as the output port. Only then I can assign this inside the always block. Then this is a behavioral description of an adder. Always add A or Bi or A or B or Ci. This is my sensitivity list. This is called a sensitivity list or a activation list. Means any change in signal A or input A here, any change in input B or any change in input Ci, this always block will be triggered for execution based on the change in this signals. Begin the always block. Sum is equal to A XOR B XOR Ci. This cap is a XOR sign. A XOR B XOR Ci. If you look at the right hand side, sum is a XOR of the three inputs. So I have to implement these equations basically here. Cout is equal to A and B, logical OR with B and Ci, logical OR with Ci and A. So this AND gets the three inputs in pairs will be ANDed, then OR to get a Cout value. So this gates equation will be implemented here. End always block end module. So what we're doing here is ignore this comment for now. So what we're doing here is we are implementing this 4-bit full adder using a behavioral model. Why is this called behavioral modeling? Because we are describing the behavior of the adder set. In the earlier example, this was a structural modeling. Why? Because we are creating a structure of a 4-bit adder using single bit adders. That's why it's called structural modeling. In this case, we are calling it a behavioral modeling because we are describing the behavior of the adder circuit. We are not focused on the structural part. We are going to feed this Verilog file or this Verilog design to the synthesis tool, which will then generate this kind of netlist file, which is basically a structural netlist. Okay. Any questions? No? Hello? Hello.
Yeah,
Hello.
I can
Yeah,
hear you.
I think the audio connection got disconnected. So till what point did you hear from me? What time did it get disconnected? I can't recall.
I could hear everything, I think, till you said that you understand.
Okay. So any
Yeah, same
questions?
here.
Any questions on this particular method?
No.
No.
Okay. So please note down this slide also. This will be a behavioral model, uh, behavioral example of a full ladder. So this sum and C out, what we see in the always block, and this is another shortcut method where we can implement this adder using a single line. C out comma sum is equal to A plus B plus CI. So this single line can replace the two lines and the same full adder circuit will be implemented. That's why this is commented out at this way. Anything with two forward slash in Verilog from that point till the end of the line is a command. When you are creating Verilog files, I don't know which editors you use, but there is a free editor called Notepad++. You can Google it, you'll find it. Notepad++. It has a Verilog language syntax highlighting mode. The Verilog mode, which will help you highlight the syntax with the keywords and other things. So you can try it out. If you're on Windows, if you're on Linux, then you can use some other editor.
Okay.
I'm done.
Done.
I need a minute.
Okay, let's wait a second.
I'm done.
Okay, so we saw examples of adder where we implemented adder using structural modeling and behavioral modeling. So when you are doing modeling, basically any modeling structure can have various, the contents of that could have any of this, combination of any of this. It can have a netlist, basically which is a structural description, like we saw in the structural modeling case. Or it can have continuous assignments. There's something called continuous assignments, which you'll see in the next few examples, which are outside the always block. They are called data flow specification or data flow. They represent the data flow logic or data flow diagrams. Normally, a data flow diagram or data flow implementation will be done using continuous assign statements outside the always block. We will see Verilog operators. Then we have seen procedural blocks, always block, initial block. Always block, you can have more than one always block in a module. So initial block can only be one inside the module, but always block can be more than one. If you are having more always block, let's assume there are always block 1, 2, and 3. The logic of always block 1 works parallelly or concurrently with respect to logic of always block 2 and this logic will work parallelly with respect to logic inside always block 3. So each always block will give you parallelly executed logic. If you want inside the always block is always sequential. One line number one to end of the always block. But multiple always block with respect to each other will give you parallel execution logic. That's how you can execute parallel logic in it. Initial block can be only one. Inside the initial block is all sequentially executed from first line of the initial block till the end of the initial. Then you can have primitives, basic gates. You can have that in the module. Nobody stops you from having that, so nobody uses it anymore. Then you can have functions and tasks, which are basically subroutines in Verilog, which can be declared once and used multiple times. So your module or your modeling structure can have any of this combination. Any questions?
No.
No.
Yeah. So yeah, so this is another example of a 3-bit adder actually. Now if you see on the bottom, this is the circuit diagram that's given to us. So this is our design specification. And if you are asked to develop Verilog for this circuit, how do you do that? Now if you see on the right, on the top section, XOR gate. Now what are the different gates here? XOR gate 2-bit, NAND gate 2-bit, NAND gate 2-bit, NAND gate 2-bit. So I have XOR gate 2-bit, 2 input XOR gate and 2 input NAND gate as separate modules where there is a Y output, A and B are inputs of XOR gate. Assign. Now this is a continuous assign statement. If you see here, there is no always block. It's outside the always block. Assign Y is equal to A cap B, which is A XOR B. End module. So this is XOR. This will implement a 2-bit XOR gate for me. Module NAND 2. YAB. Output Y, input AB, single bits. Assign Y is equal to not of A and B. So this and then inversion will give me a NAND gate, 2 input. So this end module. So this will give me a 2 input NAND gate. This will give me a 2 input XOR gate. Now I created another module, which is a top level module called add 3, in which this is a port list, out of which these are output port, input ports, and some local wires. I create this structure here. Now I want 2 instances of XOR gate and 3 instances of NAND gate. I instantiate the XOR gate 2 times, give them different labels, do the port mappings. I instantiate the NAND gate 3 times, give them different instance labels, do the port mapping. First case normal, second and third case shortcut method, still allowed. So I create this structure at the top level, instantiating the XOR gate 2 times. This XOR gate has a separate module declared here. The NAND gate instantiated 3 times. NAND 2 is a separate module declared. After that, end module. So this is how you create hierarchical components in Vim. Each gate or each module can be separate, which can then get instantiated at the top level and we do the necessary interconnections using the port mappings. Okay.
Okay.
So this gives you a full view of how separate modules can be declared and which can be then used for instantiation purpose, and we create a hierarchical design, a bigger design out of smaller modules. And this can be extrapolated. I mean, this is a basic gate, but this can be extrapolated to any complication level or any level of logic. So it doesn't have to be a basic gate. It can be bigger modules. It can go up to a very high or complete processor level basically. Okay, so we talked about primitives. So these are the various primitives that are part of Verilog primitive library. Primitives means basic gates. So the primitive gates are basic gates: and, or, not, buffer, XOR, NAND, NOR, XNOR. Then there is a buffer for with basically pull up and pull down, and inverter with pull up and pull down. So mostly nowadays, first of all, nobody uses basic gates in the design. The synthesis tool will take care of. You don't instantiate the gates directly. All you do is what you did here: A XOR B, A and B, or A NAND B. Will give me the synthesis tool will directly implement the XOR gate or NAND gate in that case. You don't have to instantiate that XOR gate separately. This was just an example. I could have directly did it here. I mean, using certain wires and other things. So this is just an example. Nobody instantiates a gate anymore. People just most of the time. Now, since we talked about modeling methods, two types of modeling methods: structural modeling and behavioral modeling. About 90% of your time, 90% of your Verilog will be done using behavioral modeling. Why? Because it's easy to do. It's easier to describe the behavior of the circuit. And that is what actually Verilog is supposed to do. It's a hardware description language. So we are describing the hardware circuit. Most of the time you're going to use the behavioral method. Only sometimes you're going to end up using the structural method. That too normally we talked about IP core design earlier. IP cores are basically smaller designs, intellectual property codes or smaller designs that you license from some third party vendors or third party companies. And those small designs or those IP cores are then integrated as a part of the complete design that you're doing. Those IP cores are provided in two formats. They can be provided with a Verilog source code, or they can be provided in a netlist format, structural netlist format. If it is a structural netlist format, then you have to integrate that structural netlist in your design at the top level somewhere. That is one area, or that is one reason why you might end up using structural modeling. It's a question of economics. Source code, Verilog source code IP is costlier. Structural netlist IP is relatively cheaper compared to Verilog source code. So some companies prefer getting a structural netlist, and then that is integrated in your design. To integrate a structural netlist, you might have to use structural methods, as we saw earlier. But most of the time, you're going to end up using behavioral method, where instantiating basic gates and other stuff, nobody does it anymore. This simple behavioral description, or the like what we saw earlier here. This is what people you will use as a designer going forward. Okay.
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 So like a two input NAND gate, you can have various other primitive gates as a part of library, like a three input NAND gate, a four input NAND gate, etc. It depends on which library you are using. You are not worried about it. The synthesis tool will implement whatever is required. If it sees that if the synthesis you are described in Verilog, now for example Y, this is Y and A, B, C are inputs. Now if I declare my Verilog code in such a way that Y is equal to, assign Y is equal to inverted or tilde, the sine wave, bracket A and B and C, bracket close. So it sees that if I feed this Verilog to a synthesis tool, it will see it needs a three input NAND gate. So if there is a standard three input NAND gate available as a part of the primitive library inside the synthesis tool, it will pick up this component from the library and use it. If not, it will use two input NAND gates and then combine them to get a three input NAND gate, like what we saw earlier, a couple of lectures ago. Similarly, you can have a standard four input NAND gate. Sometimes you need it, so it becomes a part of the library. This is all provided to you as a part of the software tool, the ISC software. Once you download it, this will all be part of the internal libraries. You don't have to worry about it, or you don't have to install it separately. Your operators, okay. So any questions so far?
No.
No.
Okay, so operators we'll see next time. That's a slightly different topic. So I want to start it next time. So next lecture will be on Wednesday, same time. Okay.
Okay.
So is this
Okay.
okay? The speed that we're going at, is this okay? Too fast, too slow? Anything that needs to change?
This is fine.
It's okay for me. It's okay for me.
Okay. If you feel at any point of time it's going too slow or too fast, or if we need to change something, let me know and we can try to change. Okay.
Okay.
Okay.